Welcome to the first episode of the Brain to Mind podcast, the podcast that takes you inside the minds of cognitive neuroscientists, sharing their science and their stories right here at the CCNS at the University of Salzburg. Did you ever find yourself saying what a friend was about to say before they even said it? That is your brain predicting what's next based on what it already knows. And it does something similar all the time, but whether and how our brain make predictions during sleep is still a hot topic in science. Today's guest is exploring exactly that, along with a whole range of other fascinating questions about the brain. And he also is no stranger to this podcast mic. Quite often, he will be the host guiding the conversation. But today, we flip the script. We'll explore his journey through neuroscience, talk about his research and get a bit deeper into science communication. So welcome, Dr. Pavlos Topalidis.
Thank you, Eva. Thank you for the nice introduction. It's a bit weird to be on the other side of the table, but I think it's equally enjoyable.
Yeah, no pressure, but...
No pressure.
Yeah. Also, no special treatment here for you.
No special treatment.
So, as we'll do every time, let's start at the beginning with your education, at the beginning of your academic journey. Many scientists find their way into research somewhat by chance or decide only later on that they want to do a PhD. But you already knew from a very young age that this is what you wanted, become a researcher. Can you remember what sparked that decision and interest in science generally? Was it a teacher? Was it a book? Was it a personal experience?
Nice. Actually, it's not true that I wanted to become a researcher. I knew from early beginning that I will do investigative work. So I was really into detective stories and crimes. I loved using my brain. When at some point in high school, I remember I was in a mathematics class, and we were doing some fancy exercise and stuff like that. And I was thinking, yeah, it's cool. Like mathematics is cool. Using your brain is cool, but you should do it for a better good, for humans. This is where the psychology topic came for me in my life. And then, I was very convinced from early age that if I study behavior, if I study humans, I have to do it through mathematics, through more objective ways. Not through actually, classical humanitarian approach where you read essays, this approach was not really my cup of tea. I'm coming from Greece, and in Greece, psychology, I think still today is quite dominated by the humanities. So you read a lot of texts, you are reading a lot of theories and, argumentation about why humans behave in a specific way. But for me, that was not interested. I wanted to do something more biologically driven and more mathematics and more objective. But back then in Greece, when I was telling this thing, I was, people would were thinking that I'm a bit off, But yeah, after many years now, I do exactly that, right? I'm interested in studying human behavior, but through biology and mathematics in a more objective way.
And I guess what you just mentioned most likely was the reason why you left Greece when you started studying.
Correct.
Your academic journey began with a bachelor's in psychology in Aberdeen, Scotland, followed by a master's in neurocognitive psychology in Munich, Germany, and then a PhD here at the University of Salzburg in Austria. So when choosing labs and programs, did you actively seek out opportunities that aligned with the research you dreamed of doing, or what guided your decisions?
So firstly, my decision to go to Aberdeen, I always wanted to go abroad, and Aberdeen was a really good university. It was also quite affordable for me to study there compared to go to Great Britain, where the tuition fees were extremely high. And I knew that their psychology is not viewed as in Greece. It was viewed more objectively, so it would be more closer to research methods. So actually, I remember me typing back then online before I started studying, is psychology a science? Because for me, for some reason, I wanted to do science. I wanted to do objective objective, measurements and study things in an objective way. So it was really important for me back then. So this is what drive me to apply and go to Aberdeen, where I studied for 4 years. I got introduced to psychology. I liked the methods. I liked a lot of the topics, but I had from first semester I had already an inclination towards cognition.
Okay.
So for me, cognitive psychology was the best thing. First semester, I remember we did learning, we did memory, we did sleep, we did consciousness. I was like, okay, this is me. I don't care about perception. We had a lot of perception in Aberdeen. I don't care about language, clinical psychology. I care about cognition. It's actually really nice that I go back now. So after finishing my bachelor's in psychology, I wanted to do something even more objective. And I remember me writing the application letter for my master's in Munich. And I remember writing, psychology is super interesting, but I want to have objective measures for studying behavior. And so the master's was in neurocognitive psychology, which again, we go more biology, more objective measures. So this is what drive me then to apply for masters in Munich, and I got it. And then during my my masters, I realized that I have a specific interest for sleep research. Actually, this was already back in Aberdeen when we did the sleep lecture. I could feel that I really enjoy this topic because sleep, changes profoundly your subjective experience. And I was like, there you go. This is a biological phenomena that changes your subjective experience. I didn't know how it was measured. I didn't know anything back then. So this is how, in my master's, I already had my mind towards sleep research. I did one or two actually projects sleep related. Also, my master thesis was in sleep. And then I got to know that there is a big program that it's running here in Salzburg with some really cool people around, and I have to apply. I mean, people were telling me, yeah, you have to apply to go to Salzburg. So I applied here in Salzburg, and since then, for 6 years now, I'm here.
Happy,
yes.
Okay.
Yes.
Even if you decide early on, interests can evolve. So has your idea of what it's like being a researcher changed since your early stages?
Yes, especially lately, because I feel that the more you are in a field, the less, how can I put it? It becomes you're very familiar with it. So you're losing a bit perspective sometimes. And this is what I'm struggling sometimes, I have to say. So when I was younger, I was so much more passionate about, talking about the things I'm interested in, searching. But now because you have very sharp specialization and you try to be competitive in your field, then you don't have so much time to, take a moment and go a bit back and see the big picture. Why are we doing this? Why does this matter? And this is actually why the science communication was important for me. And also being closer to people that they're not exposed to the sciences, because then I get a bit more, I get passionate again, and that's nice.
Yeah, I totally get that. Any idea what you'd be doing if you weren't a neuroscientist?
Good question. I like cooking. I don't know. That's. I think that I would be, as I said, from very young age, I was drawn towards investigative jobs. So I have a question and I'm searching to find out what's happening. A very good question. I have no idea. I have no idea. Maybe a chef.
Fair enough. Okay.
I mean, it's not related to doing investigative job, but I really like cooking and I like being creative.
Well, you can also figure out how to improve a dish.
Yes. Or exactly. Like search and figure out different combinations. Yeah.
Okay. Now I need to check my notes to make sure I don't miss anything. You are currently a research associate at the Landeskrankenhaus Salzburg Christian Doppler Clinic and Paracelsus Medical University. You're also the research and development science lead for Sleep 2, an app focused on improving sleep quality and awareness, which we'll talk about in a couple of episodes in this podcast as well. And you are the project leader of the Science Communication Initiative that includes this very podcast. And on top of that, you continue your research in collaboration with the Lab for Sleep Science and Consciousness here at the University of Salzburg. And you also teach. So quite a portfolio.
Yes, yes.
So when talking about your research today, we need to cherry pick and focus on one thing, I figured. So I'd like to bring up the work you did on prediction. When I first arrived here and people were introducing me to the team, like he's doing that, she's working on this, prediction was the one thing they mentioned when talking about you. Conceptually, prediction is something we experience in our everyday lives, I'd say. It is the brain anticipating what comes next based on patterns it recognizes. Do you have any concrete example to illustrate that we are anticipating what's coming next?
Right. So the predictions, this predictive framework of the brain is simply the idea that the brain is actually a statistical machinery which tries to find connections between things that are happening in the environment, right? You have the classical example, for instance, you look at faces all the time. So the brain is actually very prone to find faces where sometimes they are not. So for instance, if you look at the sky, you look at clouds and you see faces. The other day I saw a picture of Jesus being on a toast, because the toast was baked and Jesus. So the brain is that's the argument, that the brain is actually finding associations all the time. One really interesting example is language, for instance. So every time I say a word, the brain makes a list of different potential words that can come up afterwards. Right? It's also actually what also the language models that we're using nowadays are actually based for. So the brain is making constantly predictions about what is going to happen next based on what is happening now and what happened in the future, in the past. Another classical example is music. If you listen to a tone, you A B C D, then if you hear ABC, then your brain already predicts that D is coming. And now you take this very basic principle that usually is applied to understand how the brain understands sensory input, so information that goes from the environment to your brain, and you can apply this to any kind of level in the cognitive hierarchy, meaning you can apply this to social information, for instance. So you are having a date with someone, they are from a specific country, then this person turned out to be not very nice to you, then the next date you're going to have, if the person is from the same country, then you're already expecting some specific output, So you can take this idea and bring it around to different areas. What I usually like to say, also in the lectures, is about a phenomenon called nocebo effect, where you, for instance, how voodoo would work in Africa. Like, when you do voodoo, you go into your house, you see a doll that is being full of blood with nails on it, and then you know already that someone has deliberately put it there and wants you to harm. So if you believe now that this is going to harm you, then what your brain is going to do is going to pick up all the relevant information in order to validate this hypothesis. This you can apply this prediction and associations kind of thinking into many different levels of the world.
And we need to take it even one step further, because you're actually working on prediction during sleep. But first of all, maybe, how do you investigate something like this? Like, what kind of stimuli and tasks do you use and present? Where do these experiments typically take place?
So a classical experiment would be, imagine that you have a sentence, for instance, the little boy plays with, and then blank, and then you can have a little boy plays with sky, which doesn't make sense, right? Compared to a little boy plays with a ball. And then what you do usually is you record brain activity, and then you try to find whether the brain actually elicits different activations when there is something not expected, for instance. That would be a classical example in wakefulness, right? People are awake, you have their electrodes on the head, you have different such sentences, and then you try to figure out whether the brain would show what we call prediction error. What does this mean? That I predict something, but this something is not there, right?
Yeah.
A boy plays with sky, you know.
Yeah. It reminds me of the visual world paradigm, where it shows something similar, but looking at gaze, where you're looking.
Mm-hmm.
I don't know, do you know?
The visual, how did you call it?
The visual world paradigm.
Mm-mm.
It is, you have a screen and there's a boy and a cake and a ball and, I don't know, some other toy. And then you present sentences like, the boy will eat. And people, of course, look at the cake. But if the ball comes up, like, this is confusing. And you can tell even before cake is presented, they look at cake because they're anticipating and also looking at what the words mean. So they are expecting cake. Yeah, and it kind of reminded me, it shows very similar things, I think.
Yeah, so this is one way to study predictions, and other ways with people use. I mean, I know a lot of auditory neuroscience paradigms, because when you do sleep research, usually you use auditory cues because people are sleeping, and if you want to stimulate them during sleep, then visual inputs are not so easy. So different paradigms contain, for instance, different tones that they are played in an ordered or in a random fashion. So, for instance, an ordered tone would be, as I said before, A, B, C, D, A, B, C, D, whereas a random would be you cannot predict what tone will come after each other, so you cannot build up predictions. So there are different ways to measure this, but that's arguably, some of the most common paradigms.
Right. And during sleep, do you have people sleeping in the lab or? Exactly.
You have, there are different things, right? So I've studied predictions during sleep. So when you are sleeping, whether your brain can predict what's going to happen next. With some apparent applications, which could be, for instance, what they called hypnopedia. Pedia, I guess in Greek, I have to say it in Greek. I mean, I have to, which is actually the phenomena where you can learn during your sleep. So imagine that you're sleeping and then you have headphones, and then you want to learn Greek, for instance. And then you have Greek words playing on the background with their meaning, and then you wake up and then you start already, your Greek improves, Would this be possible? That's, imagine the ultimate application or whatever. So in order to address whether this is possible, you have to figure out to what extent, what can the brain do during people sleeping? And the first thing to see is whether they can actually hear stuff. Not predictions, like very simple auditory processing. So now we're talking, air pressure goes to your ears, and then you can hear my voice, right? And then you can interpret it, which is a higher level cognition. But first, audition needs to work. You need to be able to hear the sounds. And that was one of the first things that we tried to do, is try to say, okay, to what extent can the brain hear? And it's pretty obvious that even during sleep, even during deep sleep, the auditory cues reach the brain. So you would see the relevant auditory centers lighting up if you are stimulating something during sleep. But I think, is this still your question?
Yeah, sure. Keep on going.
Right. So first you need to make sure that people can hear. Then the question is, okay, how much can they differentiate between sounds? Is a low, I'm not really a musical person, but I will pretend that I am. Is it a low re, like a note or a do note? Is it different than a different note? Can the brain actually, the brain can listen, the auditory cue reaches the brain, but can the brain differentiate between the tones? And you do experiments and you find that, actually, there are different auditory cues elicit different cortical activations. That's the next level. Okay, now we'll go a bit deeper. Can the brain figure out when I have a random sequence of tones where you cannot predict which tone is going to come up next, right? So remember this ABCD experiment. So I play an A tone, and then the brain cannot predict what the next tone will be. So a random sequence of tones. Can the brain differentiate this sequence compared to a sequence which is an ordered sequence, meaning that when I have A, B, C, D, right? And again, the idea here is that when I have A, B, C, the moment that the brain hears C, then they need to be able to predict that D is coming.
Yeah.
So you have those different manipulations that you can do, but you have to really check at every stage of the processing what actually the brain can do during sleep in order to address the initial question, can you learn during sleep? Because being able to predict and being able to display some higher cognition abilities like predictions, it would be a good indication that the brain not only can hear stuff, but can also process them to an extent that it would be relevant for learning.
Mm-hmm. Well, listening to you, it sounds so straightforward and easy and logical.
Okay.
But were there some methodological, maybe even challenges you came across?
Yes, I mean, sometimes, what you usually have is, I remember you asked me before if I have people sleeping in the lab. Yeah, that's how the setup looks like, right? People come, they are hooked up with electrodes usually. I have recorded electrophysiology and also magnetoencephalography, where people go into a big magnet and then we can record the magnetic fields that the brain, tiny parts of the brain can produce. So they lay down, we play those tones, those sentences, those different paradigms, and then we ask them to fall asleep. We can check that they indeed fall asleep by looking at the patterns of the brain. And the moment that we see them sleeping, then again we play those tones, those sounds, and then you can do your analysis based on whether someone is awake versus someone is sleeping.
So, and are there differences? Are predictions as strong when being asleep compared to when being awake?
There are differences. Of course, in wakefulness, you display the brain has been studied very well. It's a very sensitive into different predictions. But the main finding, at least for my PhD work, is that not all predictions are the same. So when we say predictions, we need to actually also, scientifically, we need to really think about what do we mean exactly by predictions. So imagine, for instance, if you have a tone or a stimulus that's coming every 1 second, right? Something is beating, pop, pop. Then you can predict that again the thing is going to come. So this is different than predicting different content of the stimulus, for instance. So what we found in the project is that actually basic predictions, predicting the content of the sound, actually is preserved in sleep. So there is some evidence that not all predictions are gone. But what is actually fading is the ability of the brain to keep track of a global, bigger window of predictions. Because you can have predictions in a very short period of time, after a few milliseconds after something is happening, but you can also have predictions in a bigger time window. So this is what the contribution was there, that not all predictions are equal. We need to start differentiating between different cognitive processes.
You mentioned earlier that when we sleep, we're going through different sleep stages: light sleep, deep sleep, REM, so dream sleep. Do these sleep stages also influence predictions? Would you assume, if you don't know?
There are some studies that show that in REM sleep, the brain is capable of, distinguishing, for instance, music from something that is not rhythmic. So yes, in my experiment, I didn't observe something like this, but previous literature has shown that, in deep sleep, the brain is much more difficult first to penetrate and also to show some predictive abilities. Whereas in REM sleep, where the brain is a bit more active, it's a bit more like wake, it's a bit more easy to penetrate, let's say, from the outside world, then there the brain is a bit more capable. Yeah.
To get back to a bigger picture, why is it even useful for our brain to still make predictions, recognize patterns during sleep?
The classical example is that so sleep is a very sensitive state. So you are there, unconscious. You have no content most of the time. So if you're in your consciousness, you are not very responsive to what's happening around you, right? So you can be eaten, or someone can kill you. You cannot. You are in a very vulnerable state. So the brain needs to while you are sleeping, needs to have some monitoring of what's happening around him. So this idea of monitoring and being able to predict what maybe is a dangerous scenario or some dangerous input from the environment, that's evolutionary, super important. But it's not that we don't say that predictions at the level that I'm studying them in sleep serve necessarily an important function. It's more of a byproduct of the brain, right? If the brain can predict during wakefulness, maybe it can predict also during sleep. And then if this is the case, then we could talk something like hypnopathia and learning in sleep. It's not that, predicting content necessarily at this level, very high level, would have a specific function. But we could take advantage of it if it's actually happening.
True.
Learning in sleep, like easy, you're just chilling.
Oh, that would be great.
Yeah, that would be great.
Yeah.
Like, you've seen the movie Matrix, where at some point Neo, old movies, and Neo is sitting there, and then he wants to learn, I don't know, Jiu-Jitsu, I don't remember what it was, and then someone is like uploading all the knowledge in his brain. That would be could be us in I don't know, in 300 years or something.
Yeah, maybe even a bit longer.
Maybe a bit longer. We won't be around for sure. But
I'm
someone needs to start. This is how science works. You start with something, you try to figure out whether it works. You come up with some observations. Then 50 years later, someone takes it a step further, and all of a sudden, you end up something like AI, or something like super fancy. Or you're like, okay, how this is magic? How this happened? Yeah, this has been actually the first steps have been done like many years ago.
Yeah. So I'm concerned with different topics, but I was wondering, would it make sense to study differences between participants in making predictions? And could some people's brains be better at anticipating what's coming next or picking up patterns during sleep? And could that be linked to things like, I don't know, memory, or I don't want to say intelligence, but intelligence?
Yes, individual differences are super interesting. I think we need more of this, and I think we see it also in the experiment I've done, not just for the predictions, but even for the simple auditory processing. So if you take two brains, those brains during sleep will gate information at a different level. Your brain, you're one of those people that they sleep and they cannot hear anything that's happening around, and then you can have a really nice night of sleep.
Unfortunately, I'm not.
Unfortunately, I'm not as well. So I'm very sensitive, So my brain does not gate very well the information. So it allows the information to go from the environment to my cortex and being further processed. And then you see these individual differences to different people. Now, when it comes to predictions, of course, there are individual differences at this level as well, and there are also individual differences compared to taking under consideration the experience that someone had in predicting. For instance, a musician would be, for instance, in my experiment, much different than someone who has not been exposed to this auditory different, I try to avoid jargon here, like transitional probabilities, how you can transist between different tones. What are the possibilities, Their way to process auditory input is much different than people that they are not musicians, for instance.
But would this mean that this is actually a skill one could train?
Both, as always.
Okay.
I would say there is some biological foundation. There are some people who are much more sensitive than others, but also it has a lot to do with how much you have been exposed to these abilities. Now, I will give you an example. I try to break it down. It's a very technical topic, the predictions, and it's very interesting if you're into the sciences. But at some point, it gets technical very fast. So imagine you have a sequence A B C D A B C D A B C D. So you go around your life and you have, okay, I figure out this structure A B C D A B C D. So you build a template of how this structure is, right? Now, if I change the structure, if something happens in your life and things change, and now it's A, B, C, E, then you have to update the original template you've built. And again, try to extrapolate now. We don't talk about necessarily tones, but we talk about different scenarios, way to live your life, how you see, how you have conceptualized something, right? So you have to update your initial model of the world. And some people are very stubborn at keeping their own model, So this is what I've learned. This is the pattern I have observed.
Yeah.
And this is the pattern I'm going to use to make predictions, so to guide my life. Whereas some people are much more open to update their model. Does this make sense? I'm trying again to avoid jargon, but so you have predictions. You have the brain trying to make a template of the world. Use this template to make predictions, and you have different parts of updating the model you have, how liberal or conservative you are. So this, I would expect, again, some individual differences there.
Yeah.
Does this answer your question?
Yeah, it does. Very exciting, very exciting.
I tell you, it's very difficult to make like at some point predictions. In general, it's an interesting theory, and it can resonate to people that they are not in the sciences, but very fast it gets very technical.
Yeah, when I skimmed through your papers, I was a bit lost in the statistical part because there were some tests and stuff I never used. Some of them I did not even hear about. So, yeah, but we don't want to go there.
Yeah.
I mean, we both ended up here, so I guess we agree that this is very exciting stuff in generally all the science we will talk about on this podcast. But communicating these complex ideas to a wider audience can be a challenge on its own. And as both as a researcher and as the lead of a science communication initiative, I'm curious, has your work in science communication changed the way you approach your own research?
Very interesting question. Thank you. The more science communication you do, the more you think about the audience you have, that who's listening. So you are making sure that you're trying to adapt a bit your narrative based on the audience. This is what science communication actually teaches you a lot. And it's for me, it has been always interesting to take something super complex and try to really squeeze and boil down to simple terms. Sometimes this is easier than others. The prediction topic is a bit difficult, but I see that the more science communication I do, the more I start reflecting upon my own work. And I'm thinking, okay, what are the ways to communicate the work better? What is useful for the audience? And how can I communicate in a way that is, digestible, which is not easy.
I think it is a bit easier when, I don't know, giving lectures, talking to students, so you know that they're interested, but explaining science we do to someone randomly on the street, maybe who never heard anything about any related concepts, that is where it's a really big challenge, I think.
When you talk to someone who has
absolutely no clue.
Yes, that's challenging. Especially if you're doing this, every day and you use specific words, then it's very difficult to come up with new ways to express things. Yeah. Absolutely.
Journalism is kind of the other world you bridge in a way when it comes to science communication. And in journalism, storytelling is key. Can you relate this to science communication, giving presentations, writing scientific papers? Because at the end of the day, I'd say researchers are storytellers too, right?
Yes, the only problem there is that there are different schools of thought. When I started my bachelor's and I got introduced to scientific writing, they were telling us that, we need to use passive voice, for instance, be very objective.
Long, complex sentences.
Yes.
Yeah.
Very concise writing, very short sentences actually, and be very fast to the point, so don't fluff around. Now things change. Now I see, I'm also using more active voice because the idea is to take more responsibility of your work. Writing a paper, it is you say a story, but at the same time, I don't know, you try to be objective and be transparent. And this is the difficult part. How can I be transparent and communicate everything that has happened, but at the same time have a logical, coherent story, not being it too long, so because if it's too tiring, then also anyone who reads it, even an expert, will be like, okay, this is too much. So this is, I think, what we struggle most of the time.
And I see this a lot in poster actually presentations when people start presenting and they start going into so much details because as a scientist, you want to be transparent. You want to say, hey, this is what I did. This is exactly, we did this analysis, but I, included this filter, and, they go into details, and then they lose the storyline, and also someone who's listening to you, they cannot follow. So back to your question, I'm trying to apply those science communication skills into my also scientific work. And it's been super useful, I think. But at the same time, you have to know your boundaries, where to, be transparent enough, but also having a narrative.
Yeah. Having worked a bit in the media world as well, I know that scientists are the worst to interview. You hardly get any clear, easy, understandable statements out of them.
But
it's really not easy.
This has to do, I think, with first personality-wise, because most of scientists are super introverted. They don't want attention much. They don't talk much. They want to do their experiments. So first personality. Second, because they know a lot. If you know a lot, then it's very difficult to constrain yourself. If you know one thing, you are the most confident person there. I'm not going to name, they come up with a sentence and it's super super confident. This is how things are, but they don't know more. So it's knowing more is actually pretty hard.
Yeah. Getting back to scientific writing, is there something, or what do you think makes a paper engaging and memorable, even for readers within the field? Could you name something? When we're going through a paper and saying, well, this is what makes this paper a good one.
So, content-wise, I really like when the paper starts with a story. You have this a lot. People talk about, imagine that you are in a train and then you're looking out of the window and you see visual stimuli, the visual field changes. So when they put you they try to make their science actually related to you, this is content-wise something that I've noticed that, I really like this. The second thing is not related too much to content rather than to illustrations and figures. You always remember a paper that has a very clear, nice figure where the message is very, very, very clear to understand. Those two things, I think that, and also, a nice title where it puts you already it gives you the take-home message, if you have chunks of information that contain concise information and in the digestible way, that's the best.
Do you have any personal strategies or habits that help you structure your writing or to keep your story clean? Any advice you could give?
No. Just brain vomit on a piece of paper and then work it through. Something that I've done in the past, and I suffered a lot from this, is trying, when writing, I try to do too many things at the same time. Trying to do polishing, writing, expressing, logical argumentation at one go, which little I knew, I guess it was that is common knowledge for even some students. For me, it wasn't, because I've learned in a wrong way. But do one thing at a time. First, put all the ideas on the paper. Logically structure them. They don't need to look nice. Actually, they need to look pretty bad. And sometimes what I'm doing, if you ask for, advice, I'm really writing as if I'm talking. Sometimes I'm swearing when I'm writing, or I'm expressing my emotions, and this goes into the paper, and this helps me actually to unfold, to be more expressive. But then, of course, you tidy it up and you make it more like paper-like, right? So
that's a good one.
Yeah.
I'll try that next time.
I think it helps also with a bit motivation. Because if you write, or sometimes, I'm not doing it, of course, here, but when I need to come up with an example, the example is a very into-your-face example, very far-fetched. And this helps me a lot also with motivation, with okay, if we were in this totally weird context, how things would be. And this helps me thinking also. And it helps me, make it a bit more fun. Rather than, be very, very correct and very...
Generally, do you enjoy the writing process, or are you more the guy being into coming up with the experiments and doing the analysis?
I enjoy coming up with the experiment and analyzing the data. Writing, I like. My current problem is that because I have a lot of stuff on my plate, I don't have the time to really immerse in writing. Like those big chunks of time where you actually can really dive in. I can tell you that I hated writing in the past. I like in an extent that you cannot imagine. I had, we're not going into the details, but I suffered with a lot of learning difficulties because the initial stages of my education in elementary school were not well done. So I got some really bad habits, and I hated writing until I would say second year of PhD.
Really?
Yes. Okay. When I took a writing course, and then I start realizing that, hey man, you don't have to do all the things at the same time, polishing, editing, being very nice with expression, being logical. The page, that was the advice that really, really hit me. The page is there for you to think. Nothing else. The page is empty for you to develop thinking first. Then very late stage is polishing, because what is important is the idea, is not how necessarily how it's shaped, but the core thing is having a good idea and having a good argumentation. And then making it nice is actually, especially nowadays, pretty easy.
Yeah. Well, that is a good wrap up, I'd say, for today. Thank you so much for switching seats. I know that there is a lot more interesting stuff and experiences you could share, so maybe we'll have to do this again sometimes.
Anytime.
I think
I enjoyed as much as I enjoy interviewing. And I think, to be honest, this is easier. We should do it because when you're sitting there, you have to really, you have to keep track of time. You have to keep track of the answers. So if the topic is technical, you need to squeeze your brain a bit. Yeah. So this is much more easier. I will do this more often, actually.
Yeah. Okay. Let's do it. And I'm pretty sure I'm speaking for both of us when I say we are really excited to finally bring the Brain to Mind podcast out in the world.
Yes, maybe we need to do a podcast talking about actually the idea and the more details about the structure, how the idea came to be, what was also about the documentary.
Yeah.
And also we should fix a date for your podcast.
Yeah, no, we're going to do that. Yeah.
Awesome.